Hi friends, welcome to my video. I am here to talk about data science. So today's topic is naive-Bayes classification. Naive-Bayes is a simple yet powerful probabilistic classification algorithm. It leverages Bayes' theorem to predict the probability of a class based on given set of pictures. Introduction to naive-Bayes. At its core, naive-Bayes classifies data by calculating the probability of each class and selecting the class with the highest probability. First is predictive power, second is probabilistic approach, and third is diverse approach. And the first thing, Naive-Bayes thrives in scenarios where it tends to predictive the likelihood of an event or category. Probabilistic approach. It relies on Bayes' theorem to calculate probabilities and make informed predictions. In diverse application, Naive-Bayes is widely used in spam filtering, sentiment analysis, and medical diagnosis. Assumption and principles of naive-Bayes. Naive-Bayes hinges on the assumption of conditional independence among features. This means that the presence of one feature doesn't influence the probability of another feature. Bayes theorem. The algorithm applies Bayes theorem to calculate the probability of a class given a set of features. Prior probabilities. It considers the prior probabilities of each class based on the training data. Feature independence. The model assumes that all features are independent of each other. This assumption simplifies the calculation but can lead to inaccuracies in some cases. Advantages and limitations of Naive Bayes. Naive Bayes has several advantages, including its simplicity, speed, and effectiveness in handling high dimensional data. So the advantages are it is simple and easy to implement, fast training and prediction times, and the third is effective for high dimensional datasets. The limitations and drawbacks. It can be sensitive to the independence assumption. It may perform poorly with highly correlated features and can also produce inaccurate results with small datasets. Implementing Naive Bayes in R and Python. Both R and Python offers libraries for implementing Naive Bayes. The process involves loading the data, splitting it into training and testing sets, training the model, and evaluating performance. The first is data loading. It imports the data set and prepare it for analysis. The second is data splitting. Divide the data into training and testing sets. Third is model training. Train the naive-Bayes classifier on the training data. Fourth is performance evaluation. Evaluate the model accuracy on the testing data. Example of data set and pre-processing. Let's consider the data set of customer relies for a product. This dataset contains features like product rating, price, and review text. We can use this data to train a naive-Bayes classifier to predict whether a customer review is positive or negative. The first process is data cleaning. It handles missing values, removes irrelevant data, and transforms categorical features into numerical representation. The third is feature engineering. It creates new features that might improve the model's accuracy. This might involve extracting sentiment scores from the review text or creating a feature representing the customer's past purchase history. The third is data scaling. It normalizes or standardizes numerical feature to prevent bias from features with different scales. Training the naive-Bayes classifier. We can train the naive-Bayes classifier using the pre-processed data. The training process involves fitting the model to the training data, allowing the classifier to learn the relationship between the feature and the target variable, in this case, the customer sentiment. Feature value, product rating 4, price, this is one of the example of this. Evaluating model performance. Evaluating the model performance is crucial to determine its effectiveness in predicting customer sentiment. We can achieve this by evaluating matrices like accuracy, precision, recall, and FM score. This helps identify any potential bias or limitations in the model predictions. The first is accuracy, the percentage of correct classified instance. The second is precision, the proportion of true positive predictions among all positive predictions. Third is recall, the proportion of true positive prediction among all actual positive instance. The fourth one is F1 score, a harmonic mean of precision and recall, providing a balanced measure of model performance. Conclusion and key takeaways. Naive-based classification offers a straightforward and effective approach for predictive modeling. Its simplicity and speed make it suitable for a wide range of applications, particularly those dealing with large data sets, real-world applications, and handling large data sets. Naive-Bayes has proven valuable in fields such as spam filtering, sentiment analysis, medical diagnosis, and recommendation system. Its ability to handle high-dimensional data makes it suitable choice for today's data-intensive environments. Thanks for watching my video. Please do like and subscribe.